2009, got my degree. I was co-advised by both Henrik and Sid. So my research mainly on granular flow. But when I moved to my postdoc study and my current research at Minnesota, so I'm more looking into suspension, so mainly wide granular flow, right? So I'm going to say something about suspension rheology. This is actually the content I use when I give we have the short course on rheology every another year in University of Minnesota. So attendance may be mainly from industry. So here I know the audience of physicists, but now you see my affiliation, I'm in chemical engineering department, so I call myself engineers. I think I talked to John, who exchanged some email. One, I think the direction for future is, as a physicist, we should look more and more into more complicated system, right? Not ideal system that may more relate to engineering type of materials. That's why I like to give a talk on this topic. So, of course, we know all the soft materials has very interesting rheology behavior, right? At least the typical material, soft materials we can think about, one like micelles, a lot of people study that surfactant system, polymer system, entangled polymer system, colloid gel, and emulsion. So what I'm going to talk about today is mainly on suspension. So this is a really ideal model for all the other systems. So if you want to understand, for example, rheology of polymer, the first step you should do is understand rheology for particles. So yeah, that's what my focus. So when I say suspension, what I mean here, suspension mainly composed of two phases, right? Two components. You can either have solid in liquid, that's a typical either granular type of a suspension or colloid suspension. You can have liquid in liquid, that's give you emulsion blend, or you can have gas in liquid, that give you foam. And then finally, of course, you can have liquid solid, small particle in gas, that give you aerosol. A lot of them share the similar rheology behavior. So talk today, or the tutorial today, mainly focus on suspension, colloid suspension. So colloid suspension shows very complex rheology behavior. If you read the introduction or the first chapter of Doyle Edwards in their classical book, Theory of Polymer Dynamics, they are actually saying that colloid suspension is more difficult to understand compared to polymer. The reason for that is polymer, if you have a single chain, you can have many neighbors. Essentially, you can use a mean field theory to understand what happens. But if you have colloid suspension, each particle can have at most 12 neighbors, but in the random case, maybe 6 neighbors. So you cannot use a mean field type of theory to understand what happens. The fluctuation is really important in this type of materials. And of course, when we talk about colloid suspension, you can think about really broad application industry. And this form a model system to understand another non-Newtonian fluid behavior. So I give some example here where you can see colloid in nature and industry, blood, paint. In our department, chemical engineering department at Minnesota, we actually have a really big program trying to develop very good paints for companies. And food products, the colloid suspension, slurry used in drilling, petroleum industry, that's a very good suspension system. Cosmetics and ceramics, they are all colloid suspensions. So we want to understand how they flow and what's their rheology behavior. I don't know the background of the audience here. I want to really start from the beginning, very basic things. First of all, what's the non-Newtonian fluid, right? To understand non-Newtonian fluid, you should start with a Newtonian fluid. If you have water, for example, viscosity of water will be independent of shear rate or shear stress. That means that no matter how fast you shear your fluid, you get same viscosity. And if you do oscillatory shear, you will see that this is your shear strain, and your shear stress will go also sinusoidally, but with a 90-degree phase difference. That's basically tell you that water so give you perfect fluid response. When you have maximal strain rate, you get maximal stress, right? Water doesn't care how far you move the liquid, only care about how fast you move the liquid. Of course, there are many types of non-Newtonian behavior, and the 3 typical ones. The first one is shear thinning. In this case, viscosity decrease when you increase shear rate. Classical example is toothpaste. You have toothpaste in the tube, you squeeze it, it will flow, but when you stop squeezing, it will stay like solid. So it shows dramatic shear thinning behavior. Also, paint is very important shear thinning fluid. And then, of course, the second type is a shear thickening, where Henrik here did a lot of work on this. So I will leave John later to talk more on shear thickening mechanism. But I just want to point out, when you have shear thickening behavior, the viscosity will increase when you increase shear rate or shear stress. The more you shear, the more viscous of your liquid. And of course, last, you also have viscoelasticity. Mainly polymer fluid, polymer solution have this behavior. In this case, if you do oscillatory shear, you see the stress and strain phase difference more than 90 degrees. That means that fluid has both liquid response and fluid response. And this is some classical video from MIT where they show the behavior of PEO solution. This case, it's very viscous liquid. You can take it back. Because the elasticity of the solution. And second case, you can cut it. It's really like solid. So the materials can flow, but on the other hand, because the long molecule inside the solution also has some elasticity. So it shows this viscoelastic behavior. Okay, so what I want to show you today, and also John later on, is basically understand this curves here. What I'm showing you here is viscosity of colloid suspension as function of shear stress, or equivalent shear rate. So what you see here is what happens when you have a suspension of different volume fractions. For volume fraction equal to 0 means that you have just pure water, no particle at all. When you increase in volume fraction, you have more and more particle in your solution. And you can see here, when the volume fraction is small, essentially the viscosity is just a constant, independence of shear stress. Essentially have a Newtonian fluid. But when the viscosity is about 30%, you start to see some region where when you increase shear stress, the viscosity starts to decrease. You got shear thinning here. When you increase in volume fraction more, now 43% of your fluid is made of particles. You see very strong shear thinning behavior. Go even higher volume fraction, you see even stronger shear thinning behavior. And then you get this what they call second Newtonian plateau. Because at low shear rate, you have one Newtonian plateau, you have shear thinning, then you have another Newtonian plateau, this is called second Newtonian plateau. And then eventually, when you go to high shear stress or shear rate, you get shear thickening, means the viscosity will increase. And this is still mild shear thickening, so you see the viscosity still increase continuously. But if you increase the volume fraction even higher, near the random closed pack volume fraction, you can see very dramatic shear thickening effect, which John will show you later. Okay, so let's define our model here. So if we think about the real industry use, colloid suspension can be really complicated. You can have a charge between particles. You can have a lot of a polymer that introduce a depletion force, spherical force between particles. And of course, in the real industry, you can have particles of different shape. So it's a really complicated system. I don't have time today to go to those complicated systems, so I want to focus on a simple system. I call this the ideal suspension system, where there are only two things matters. One is the volume fraction. So because I will have monodispersed spherical particle, right? There's no shaped things and no steric interaction, it's just hard sphere particle. And in this case, I can define the volume fraction, which is equal to the density, the number density of the particle times the volume of each particle. A here is the radius of the particle. And now, of course, everything is in liquid, I still have hydrodynamic interaction between particles. And if I combine Brownian dynamics timescale, tau b, how fast a particle diffuse under the influence of Brownian motion, time that with the shear rate, I can build up this what they call Patet number, essentially a dimensional shear rate, compare the shear timescale with Brownian diffusion timescale. So this is the two relevant parameters in my system. So out of these two parameters, I can understand shear thinning, and I can understand viscoelasticity, and later on, John will tell you shear thickening in this ideal system. So let's start from beginning, because we're talking about small particles, micron size or below. If you write hydrodynamic interaction between particles, Navier-Stokes equation will be simplified into a Stokes equation. We don't have any inertia because Reynolds number is really small. This is called creeping flow. And this is just one visualization of the flow around a single particle, where you can see the flow just passing through the particle. You have a perfect symmetrical flow in the front and behind the particle. And actually, you can do the calculation. This is the calculation at low Reynolds number. You can know the velocity field around this particle and also pressure field around this particle. Some complicated equation here. And the important thing you know is the velocity actually decay as 1 over r, pressure decay as 1 over r squared. So there's a long-term, long-range interaction between particles in the fluid. the first calculation actually done by Einstein. And this is probably the most cited work from Einstein, not relativity. This is actually more important for real life application, right? So Einstein do this calculation. It's actually not very hard calculation because you already know the velocity field and pressure field around single particle. You can easily do the integral. This is the shear stress on the surface of particle. You do the integral around the single particle there, and then you can calculate how much shear stress you will have on the particle. And then you assume that you have very dilute suspension, means that they don't talk to each other. The flow disturbed by this particle won't influence flow in front of this particle. They're far away. And in this case, you can just add them together, right? And just do summation. And Einstein did this calculation. The first one published in 1906, something wrong in the prefactor, and he corrected the error 5 years later. And the answer, the solution tell you that the viscosity of the solvent, the viscosity of the suspension, eta, equal to the viscosity of the solvent times 1 plus 2.5 phi. Phi here is volume fraction of the particle. And the really interesting result here is that this phi is independent of the shaped particle. You can have any shaped particle, you just need to calculate the volume fraction, you get the same result. And of course, there's no shear rate dependence. No matter what shear rate you have, you get this same result. So this basically tell you what happens at this low shear limit. When the shear rate goes to approach to zero, how the viscosity change as function of volume fraction. And this happens when the volume fraction is small. When your volume fraction is smaller than 5%, actually even between these two curves, Einstein relation works. When you go to higher volume fraction, this will break down. And to correct those things, to understand what happens when the volume fraction is higher, actually you need to think about hydrodynamic interaction between particles. Now you can see the flow disturbed by this particle will influence the flow on the second particle. Now you have hydrodynamic interaction between two particles. And the guy who did the calculation goes to the second order, is a bachelor, and this is very tedious calculation, I would say. Through that calculation, you can show that when the volume fraction is more than 10%, you can have this second order term. Essentially, this tells you the particle-particle interaction. That's why it's a phi square, and the prefactor here is 6.2. And in principle, you can go to higher and higher order when you go to higher and higher volume fraction. You can have 3 particle interaction, 4 particle interaction, so on and so forth. But as far as I know, no one calculates C3 or C4. It's too complicated above the paired interaction. So there's some empirical result. I don't have time to talk about it here. The essential idea here is that when you add more particle into your solution, you can treat the particle added into a continuum fluid. Even though you already have particle here, but you can treat the whole thing as one fluid with some viscosity eta, which is function of phi, and then you can use Einstein's idea to continue your calculation. If you just go through this logic, it's really a phenomenological way to think about the problem. You can actually get this formula here, this very famous equation used a lot in engineering community called the Craig-Dougherty equation. What you have here is the suspension viscosity go as a solvent viscosity times this factor here, 1 minus phi over phi maximal minus intrinsic viscosity, which is 2.5 from Einstein, and then you have a phi maximal. This phi maximal is a maximal volume fraction you can pack, maximal number of particles you can pack in your solvent. So you can see when phi equal to phi maximal, this viscosity diverge, which makes sense because now you have so many particles, essentially the whole system jammed. Right? Then the question is, what's the maximal packing you can have? In 3D, of course, if you have older structure, the maximal packing will be 74%. But if you have a random pack, the maximum volume fraction will be 64%. So empirically, you can put the 0.64 here, 2.5 here, 0.64 here. You can get pretty much good guess of what's your viscosity. But in reality, when your phi is very close to phi maximal, even this equation is not going to be good. Okay, so I go quick here. What I'm trying to tell you so far is we can have some good understanding of what happens in this part of the curve when the shear stress approaches zero, how the viscosity increases with the volume fraction of the particles. And the next thing I want to talk about quickly is what happens when you have shear thinning. Why you can have shear thinning in colloid suspensions. And again, some empirical result. Engineers summarize all this for a long time. What you have here is that you can have the low shear viscosity and second Newtonian plateau, and in between you have shear thinning, and you can use this what they call cross model to phenomenologically feed the data. Right? There's a free parameter here, eta, sigma c. Okay, so I want to go to the mechanism here. I skip some slide because I don't want to take too much time. We want to talk about shear thinning too. So the general idea why you have shear thinning. The reason why you have shear thinning is really because your shear compete with Brownian motion of the particles. Everyone know Brownian motion. I don't need to tell about this. But the general idea is that in the equilibrium, your particle maximize the entropy, minimize the free energy, and you apply a shear strain here, you perturb your system, you drive your system out of equilibrium. And then your entropy decrease, your free energy increase. But after certain relaxation time dictated by the Brownian motion, your system will relax back to equilibrium configuration. Now you go back to original configuration, or the configuration where you have maximum entropy, and the actual free energy you generate when you shear will dissipate, and this dissipation essentially give you the viscosity. That's give you the shear thinning behavior. So the general idea here is that if you have your Peclet number, which compare the shear timescale with the Brownian timescale, when Peclet number is smaller than 1, that means that your Brownian motion dominant your behavior. Then you got zero shear Newtonian plateau, which is the one that I talked about before. But when the Peclet number is much bigger than 1, then the shear or hydrodynamics force dominant the system. You go to second Newtonian plateau, you get second type of viscosity. And when you have the transition between the two, when Peclet numbers are older than 1, shear thinning occurs. Right? Again, Peclet number is the key parameter here to control shear thinning. That's basically compare the two time scale you have in your system. And some experimental result where you have a G prime, G double prime, the sum of these two and divide by omega give you the viscosity. You can see there's a first viscosity here, second viscosity here. So this part will be the first Newtonian plateau. This part will be second Newtonian plateau. And in between you have shear thinning behavior. Very small, but you transition from one slope to another slope. The slope here gives you the viscosity of the two regimes. Just the last thing here is that actually you can look your system by looking the structure of your particle under shear. As you can see here, when I have small Peclet number, when I look the distribution of the particle with respect to a reference point, I have uniform particle distribution. Because in this case, Brownian motion is still dominant. I have a uniform isotropic particle configuration. However, when I increase Peclet number higher and higher, when my shear gets stronger and stronger, you can see I concentrate more and more particle along this 45-degree direction. That's essentially because you shear your sample, you compress particle closer and closer along this 45-degree direction. And your Brownian motion is not strong enough to overcome this shear force, and then you concentrate all your particle there. And if you do the calculation of shear stress based on this structure here, you can actually get shear thinning behavior. Just some of our work, my work when I was a postdoc at Cornell. So I can show you the real behavior. So this one is what you have when you shear your sample, you look at particle configuration inside your suspension. And the most interesting one, of course, is this one. Because I shear along x direction, my vortices along z direction, my shear gradient is along y direction. So you can imagine I have two plates here. I put my particle between the two plates. I'm moving the plate back and forth, one plate back and forth. I look from side, and I look how my particle kind of tumble or rear-ended under shear. That's basically what you see here. The color here basically just tell you the probability to find a particle at those locations. The brighter the color means the higher probability you'll find a particle there. And in this case, when you have a low Peclet number, essentially your dynamics doesn't change, or your particle configuration does not change as function of time, and you get this more or less symmetric configuration. However, if you go to higher Peclet number, you go to this case. Now, if you look carefully here, you look at your particle configuration in this shear plane, you see this one oscillated back and forth. The reason why it's oscillated is because I do a surface shear. I move forward and I move backward. When I move forward, I compress the particle along this 45-degree direction in this case, so I will see rain tilting along this direction. But when I move backward, I will push particle along this direction. I will see elliptical compressed configuration along that direction. That's how I get this oscillation here. So I hope through this very quick kind of introduction, I can tell you why we get shear thinning. Shear thinning is really due to the computation between shear and burning motion. And we have a first Newtonian plateau, where Einstein relation can tell us, plus some corrections can tell us what we have here, and then we have second Newtonian plateau. Now the next one is what happens when you go to even higher shear rate, when you get shear thickening behavior. So for that, I will pass this to John.